Hello, and welcome to our segment on the Higgs boson. I remember back in high school, a long time ago, when we were learning about magnetism. I was particularly impressed by what could be going on at a point here, far from the actual magnet, that could move an object like an iron filing. I think it was my curiosity back then that led me to the Math Institute at Oxford, where I studied the mathematical foundations for quantum field theory, which is the theory of what's going on in this so-called empty space. If we can get a deeper understanding of the nature of force in space, distant from a particle, we'll have what we need to know in order to get an understanding of the Higgs boson. We saw in our first segment that particles with electric charge create an electromagnetic field around themselves that stretches out in all directions. This field is attached to the particle. It will go where the particle goes. In quantum field theory, fields like these are quantized. That is, they contain tiny, massless, energyless bits of the field. We have seen that the photon is a certain type of disturbance, an excitation or vibration in the electromagnetic field. We'll call these a localized vibrating ripple. It moves with a life of its own. It is not attached to the particle that created and sustains the field. Now we take a little leap. If a photon is actually a localized vibrating ripple in the quantized electromagnetic field, why not consider the electron to be a localized vibrating ripple in a quantized matter field, a field that permeates all the space in the universe? This is not as odd as it might look. In our first segment on the microscopic, we saw the wave properties of the electron. And in the second segment on the atom, we saw that its behavior is described by the Schrödinger wave equation. And in our third segment on elementary particles, we saw how electrons and positrons can be materialized at any point in space. What's happening is that the photon has disturbed the electron field to the point that it generates the kinds of waves that constitute electron particles. A convenient way to illustrate elementary particle interactions is to use Feynman diagrams invented by Richard Feynman in 1948. Straight lines are for fermions. Squiggly lines are for force particles, bosons, and the back arrow on a fermion indicates an antiparticle. This is what quantum field theory is all about. In modern physics, there is no such thing as empty space. Fields pervade space. They are a condition or property of space. You can't have space without fields. Here's a couple of examples of how this electromagnetic force works. When two electrons approach each other, their charge generates a disturbance in the electromagnetic field. This disturbance pushes them apart, and their paths are bent outward. The same is true if an electron and a positron pass near each other. The disturbance in this case is similar in type, but different in its details, with the result that the oppositely charged electron and positron are attracted to each other. Their paths are bent inward. Here's the Feynman diagram for an electron-electron interaction, where the photon field mediates the force that changes the momentum of the two electrons. One says they exchange virtual photons, but this is just jargon. The diagram is used for convenience. A virtual particle is not really a particle at all. A particle is a nice, regular ripple in a field, one that can travel smoothly and effortlessly through space. This virtual particle is a disturbance in the field that will never be found on its own. It doesn't have the energy to become a well-formed ripple moving through space. This kind of disturbance will decay or break apart once its cause is gone. This kind of interaction between electromagnetic fields and the electron field is important because the force that the two charged particles exert on each other is generated by this interaction. This became the model for the other forces of nature. The complete picture of what is going on with electromagnetism is still an area of active research called quantum electrodynamics, or QED for short. So using QED as the model and data from thousands of high-energy scattering and collision experiments over the past 20 years, we have come to the following understanding about quarks. Quarks are the strong force equivalent of electrons, and the gluons that bind them together are the strong force equivalent of the photon. A quark is a vibrating ripple in the quark field that permeates space, just like an electron is a vibrating ripple in the electron field that permeates space. Electrons carry the electric charge that generates an electromagnetic force field. Quarks also carry electric charge, so they too generate an electromagnetic force field. Although with only 1/3 to 2/3 of a charge, their electromagnetic force field is weaker than the electrons. But it turns out they also carry a different kind of charge we call color charge. This charge generates a gluon force field. We have seen that an accelerating electron creates a vibrating ripple in its electromagnetic field called a photon. Similarly, an accelerating quark creates a vibrating ripple in its gluon field called a gluon. And where photons can accelerate electrons, gluons can accelerate quarks. And where an energetic photon can create an electron-anti-electron or positron pair, an energetic gluon can create a quark-anti-quark pair. And where interacting electrons disturb the electric field in a way that causes virtual photons that exert a force on the electromagnetic field, interacting quarks disturb the gluon field in a way that creates virtual gluons that exert the attractive force of the gluon field. So you can see that there are a lot of similarities between the electromagnetic force and the strong force. One of the key differences between them is that the electromagnetic charge has only one version. The color charge has 3. But color charge never shows up in hadron-quark combinations. This is what led to the idea to use the colors red, green, and blue, because they add up to a neutral white. Another, even more dramatic difference between photons and gluons is that gluons carry the same color charge as quarks, whereas photons do not carry the electric charge. This enables gluons to not only interact with quarks, but to also interact with each other. Here we see a gluon carrying away a green and anti-blue charge, changing the quark's charge from green to blue. It carries this combination to a quark with a blue charge, changing it to green. Our very idea of what a proton looks like has now shifted from a point particle to a 3-part particle to a whirlwind of elementary particle activity. In fact, it is very difficult to distinguish between the disturbances that represent virtual particles and disturbances that represent actual particles in a plasma like this. But for our purposes, we can view a proton as a cloud of gluons holding 3 quarks together. The proton is key to helping us understand the origin of mass. The only stable elementary particles in the proton with mass are the 2 up quarks and 1 down quark. Their tiny masses constitute only 1% of the mass of the proton. 99% comes from the energy of the fields and motion of the moving parts following the famous E = mc² formula. So it is quite accurate to say that confined energy is the origin of mass. We'll bring this point home when we get to the Higgs boson. One more critical difference between the electromagnetic force and the strong force is that the strength of the strong force is huge, over 130 times stronger than the electromagnetic force inside protons and neutrons. As the distance between quarks grows to the diameter of a proton, the strength of the force approaches 18 tons. Imagine 18 tons focused on such a tiny spot. This makes it virtually impossible to separate quarks. One last item on the strong force answers the question I raised at the end of our segment on the atom. What holds the protons together in the nucleus? In 1934, the Japanese physicist Hideki Yukawa made the earliest attempt to explain the nature of the nuclear force. According to his theory, a particle was being shared between nucleons, like molecules share electrons between atoms to bind them together. Here's a two-proton example of how we think it works. First, in one of the protons, an energetic gluon spontaneously creates a down quark, anti-down quark pair. Next, the pion drifts into the other proton, and the anti-down quark annihilates a down quark, leaving the other down quark to take its place. The study of quarks, gluons, and their color charges is called quantum chromodynamics, or QCD for short. It is a very active area of research, and changes in our understanding are expected as we learn more. The weak nuclear force, or weak interaction, is responsible for radioactivity. For example, beta radiation ejecting electrons and neutrinos. It's the force that turns a neutron into a proton. Unlike quantum electrodynamics and quantum chromodynamics, there is no separate matter field that creates a particle with a weak force charge, sometimes called weak isospin or weak hypercharge. Instead, all fermions already have this charge, including electrons, quarks, and neutrinos. Like accelerating electrons and quarks create vibrating ripples in their respective force fields, called photons and gluons respectively, accelerating electrons, quarks, and neutrinos can create vibrating ripples in the weak hyperfield, called W+, W-, and Z particles. They are spin 1 particles, making them bosons. They are the force particles for the weak interaction. And when interacting electrons and gluons disturb their respective force fields, creating virtual photons and gluons, interacting particles with the weak hypercharge disturb the weak hypercharge field, creating virtual W and Z bosons. We call it the weak force because its coupling constant is 3.3 million times smaller than the strong force coupling constant. And unlike massless photons and gluons, these particles are massive, around 50 times more massive than an up quark and 160,000 times more massive than an electron. This makes the range of the weak force around 0.1% of the diameter of a proton. The weak interaction can change one flavor of quark into another. The idea that a field can cause a particle to decay was a new one. We'll use beta decay from our radium to polonium energy experiment to help illustrate how this works. The process consists of 2 phases. The first phase is similar to the way an electron emits a photon when it drops to a lower energy state in an atom. Here, a down quark drops to a lower energy up quark and emits a W boson. However, the mass of the weak field quantum is so large that there is not enough energy in a down quark quantum leap to an up quark to create a fully independent W boson. Instead, what is created is a virtual W boson. However, in the second phase, because there is enough energy in the virtual boson to create an electron and a neutrino, it decays into these particles. This is possible because both the electron and the neutrino carried the weak hypercharge. This is how our radium turned into polonium in our segment on the atom. Here's the standard model with all the stable fermions. If we add the excited state versions of these fermions, we get the full view. All of space is filled with matter fields that can spawn fermion particles as waves. This includes all the leptons and the quarks. These particles carry one or more charges: color charge, electromagnetic charge, and weak hypercharge. Particles with a charge fill the space around them with a force field that can spawn force particles when excited by particles that carry their charge. These are the bosons. The bosons are the force carriers or mediators of all fermion-particle interactions. This model has had great success in explaining observed natural behavior at the quantum level. But there was one serious problem that had to do with the mass of the particles. One way to look at it is that it didn't explain how elementary particles acquire mass. In classical physics, mass is a measure of the inertia of a body. The mass of an object causes it to resist a change in its speed or direction. The greater the mass, the greater the resistance. This is codified as force equals mass times acceleration. In quantum field theory, on the other hand, the energy of a quantum is represented by oscillations in its field. Since both mass and energy are associated with oscillations in the particle field, we can simply combine Einstein's equation for mass energy and Planck's equation for wave energy to calculate the mass of a wave. The faster a particle is oscillating, the harder it is to change its direction or speed. So this fits our common understanding of mass. Paul Dirac identified the oscillation of a particle between its right-handed incarnations and its left-handed incarnations as a mechanism for fermion mass. The faster the oscillations, the more energetic the particle, the more massive it is. It might seem strange, a particle changing its spin on the fly. But if you recall that particles travel as waves, and spin can be viewed as a phase shift in the wave, it's not too hard to visualize. We'll use electrons as an example. A left-handed spinning electron has a spin 1/2 and carries a weak hypercharge. A right-handed spinning electron has a spin of -1/2 and carries no weak hypercharge. So for an electron to switch from left to right, it must emit a quantum of weak charge and lose a full unit of spin. And for it to switch back, it must absorb a quantum of weak charge and gain a full unit of spin. Now here we had a very large problem for particle physics. It was understood that a derivative of the Z boson was a candidate for the electron spin and charge transition. But there was no standard model mechanism for ejecting and absorbing weak hypercharge out of the blue. Where did the charge go? And where did it come from? In 1964, in order to resolve this problem, Francois Englert, Robert Brout, Peter Higgs, and others proposed a new field that permeated all of space, now called the Higgs field. They proposed that this field contained a condensate of weak charge. A condensate has the property that adding to it or subtracting from it leaves it the same. A particle carrying weak charge could use a weak charged virtual Z boson to move the charge to this condensate without noticeably changing the field. And it could use the same Higgs boson mechanism to absorb a weak charge from the condensate without noticeably changing the field. This was called the Higgs mechanism. With the Higgs mechanism, an elementary particle that carries a weak hypercharge can oscillate and therefore has mass. Electrons, neutrinos, and quarks all carry this charge and interact with the Higgs field, so they can oscillate, and therefore they have mass. Photons don't carry weak hypercharge, and therefore they cannot interact with the Higgs field, and therefore they cannot oscillate, and therefore, no matter how much energy they may have, they have no mass. The process is a little different from particle to particle, and physicists use subtler concepts of chirility, gauge symmetry, and symmetry breaking, but this is the basic idea. You'll note that the particles that interact with the Higgs field are not slowed down. The Higgs field is not like molasses. If the Higgs field slowed particles down in any way, objects in motion would no longer remain in motion. This is not what we see in the real world. Here's one more important idea about mass. The reason the masses are different for different particles is that the coupling strength of the interaction with the Higgs field is stronger for some particles than others. Increasing the coupling strength is like increasing the stiffness of the spring in a harmonic oscillator. It has the effect of increasing the oscillator's frequency. And we have already determined that if we increase a particle's oscillation frequency, we increase its mass. Now we can ask, what is a Higgs boson? We have learned that, under the right circumstances, excited fields generate particles. This also applies to the Higgs field. If it exists, it has an associated particle. That particle is called the Higgs boson. So working in reverse, if we can find the Higgs boson, we'll have strong evidence that the Higgs field exists, and the Higgs mechanism is real, and the standard model of particle physics is correct. But it turns out to be quite hard because the Higgs particle is very massive, around 133 times more massive than an entire proton. It requires a great deal of energy to form one. At the time the Higgs boson was proposed, no existing accelerator could do the job. This is why the Large Hadron Collider at CERN was built. It has the world's largest and most powerful particle accelerator, called the Large Hadron Collider, or LHC for short. Using hydrogen with the electrons removed, proton packs containing billions of protons are accelerated down a linear accelerator like we saw at SLAC. The first booster accelerates the protons to 91.6% of the speed of light. The protons are then flung into the proton synchrotron. They circle here for 1.2 seconds, reaching 99.9% of the speed of light. The protons are then channeled into the superproton synchrotron. Here they are accelerated to the point where they can enter the Large Hadron Collider. Here, there are two pipes that carry the proton beams in opposite directions. Each beam is accelerated to 7 tera-electron volts. That's 7 trillion electron volts. And because they are traveling at each other, the total energy of a collision is 14 trillion electron volts. This ought to be enough to kick the Higgs field into producing a Higgs boson. As the protons approach each other, they are traveling at 99.999999% of the speed of light. The actual collision creates hundreds of particles that scatter out in all directions. Detecting and measuring the trajectories, momentum, and energy of each of these particles is the next big step. For cross-checking purposes, CERN uses two main detectors. One of them is the Compact Muon Solenoid, or CMS for short. CMS weighs around 14,000 tons. The second detector, called Atlas, uses a different technical solution and a different magnet system than the one designed for CMS. The detector has a number of components, each designed to detect a particular kind of elementary particle. The LHC creates around 600 million collisions per second. Of these, only a few create particles massive enough to be interesting. Massive particles decay into lighter particles so rapidly that we cannot see them directly, but we can detect the lighter particles created by their decay. We can then deduce the original particle by their decay signatures, just like we did in the cloud chambers on mountaintops in our segment on elementary particles. On July 4th, 2012, 45 years after Peter Higgs proposed its existence, CERN announced that one of these interesting particles, created in a 2011 collision, turned out to fit the decay signature for the Higgs boson. In our search to find out what is actually happening at that point in empty space outside the magnet, we have learned a lot. We have discovered that empty space is a complex entity. It can be stretched, as seen in the expanding universe. It can be bent, as understood by general relativity. It's filled with various types of matter fields, force fields, and the Higgs field, according to the Standard Model. The elements of these fields are quantized, massless, and almost energyless. And we know that empty space offers resistance to change in these fields, for example, permittivity and permeability. We know that with enough energy, the elements of a field can bunch up into localized particles with properties like mass, spin, and various types of charges that spew out their own field elements into the empty space around them. But as much as we've discovered, it feels like we're still just scratching the surface. The order in the Standard Model, like the order in the periodic table of the elements, lends itself to the theory that there is an underlying structure yet to be discovered. This, along with the mysteries of dark matter and dark energy, plus the fundamental incompatibilities with general relativity, also speak to a deeper reality. String theory, supersymmetry, and loop quantum gravity are just a few of the candidate theories currently being explored. In that vein, as we approach the end of our How Small Is It video book, we'll take a look at the smallest that small can get. In quantum mechanics, there is a minimum length called the Planck length. It is over 62 trillion times smaller than a neutrino, our smallest elementary particle. This Planck length is as many times smaller than this dot, as this dot is smaller than the visible universe. Theoretically, it is impossible to determine the difference between two locations less than 1 Planck length apart. This idea takes us back to our first segment on the microscopic, where we saw how light diffraction created the same problem for optical microscopes. As we pointed out at the start of our story, you can't probe a grain of sand with your finger. How are we going to find out what's happening at this Planck level, the level where the quantized field elements operate? This is just one of the many challenges for physicists of tomorrow. It should be interesting. Please take a look at the credits segment. It will point to other resources for additional research. Thank you for watching.